All right, so today we're going to look at section 5.3, which is on the medians and altitudes of a triangle. So we already talked about perpendicular bisectors. That's where you circumcenter. We talked about the angle bisectors. That's where you get your in-center. Let's take a look at the medians. So the median is another segment we can draw in a triangle, and it's drawn from a vertex to the midpoint of the opposite side. Okay, so it looks something like that. We've got a segment coming from the vertex, going to the midpoint of the opposite side. How do I know it's a midpoint? Well, two ways. One, I wrote D as the midpoint. And two, I've marked segment BD and segment DC as congruent. That also shows it's the midpoint. So if you draw in segment AD from a vertex to the midpoint, AD is a median of triangle ABC. Okay, any questions on that? That's a median. So depending on the kind of triangle you have, sometimes a median can be the same as a perpendicular bisector. Could also be the same as an angle bisector. Could also be the same as an altitude. Right? In an equilateral triangle, a lot of these things do overlap. Okay, and they become the same. I'm going to try to look at triangles that aren't special cases, where all those points would be distinct. Okay, what do you think about the median? Okay, we learned a little bit about the concurrency, and these lines are concurrent. Okay, the name of the point where they're concurrent is called the centroid. And what do you think about that? Do you think the centroid would always be inside the triangle? Could it be outside the triangle? On the edge of the triangle? What do you think?
Inside.
You think it's always going to be inside?
It's all inside.
You think it could be all three, like the circumcenter? Depends on the type of triangle? Okay.
It's on the inside towards the middle.
On the inside? Okay. It is always inside. Okay, the centroid is always inside, and there's a good reason for that. I'm going to explain in a second practically what the centroid is. And then it'll make perfect sense, like, oh, of course, it always has to be inside. Centroid is it's a special point, like physically, on the triangle. Okay, so let's look at the three cases. So I have an acute, a right, and an obtuse triangle. Same three cases we looked at for the circumcenter. Okay, in an acute triangle, notice it's inside, right triangle, still inside, obtuse triangle, inside. Anybody have any idea what that point is physically in terms of the triangle? It's not the center of a circle that goes through the vertices or is inside the triangle. That's the circumcenter and in-center. But this point is special. Anybody have a thought? Can you be more specific? What do you mean by the center of the triangle? Equidistant from all the vertices? So, there is a point that does that. And I know you weren't here yesterday, so that's a good guess. But does anyone remember what's the point that's equidistant from all your vertices? That's the other point from yesterday. That's your circumcenter. It's equidistant from all the vertices. This one's not. I think the clearest one to see that in is the obtuse triangle. Look at the distance between here and here, and then say here to here. Big difference. Any other thought about that, Denver was kind of on the right track when he said the center of the triangle. Have a thought? If not, I'll try to help you out.
Is it equidistant to each of the sides?
Well, that's also something else, but that was yesterday. That's the in-center. Think about if you had a circle in there, and you're equidistant to each side, that's your radius. So no, it's not equidistant to the sides. Let's see if we can look at that. Look at this side, look at that length versus, say, measuring that length there. A little bit different. All right, let's take a look and see if we can figure it out. Well, first of all, mathematically, this is what the centroid is. The medians of a triangle intersect at a point that's 2/3 of the distance away from the vertex towards the opposite side. Right, so in other words, let's see if I can show you. Okay, let's take this obtuse triangle, move it down here a little bit. Let's see if I can make it a little bigger. Two-thirds, the medians intersect at a point that's 2/3 the distance from the vertex to the midpoint of the opposite side. So let's look at the segment right here. Okay. Segment A, B. That's a median. It's drawn from the vertex right to the midpoint of the opposite side. Let's say segment AB was 15 units long. If the medians intersect at a point that's 2/3 of the way toward the opposite side, what that means is, let's call this point C. Okay, if you're looking at segment AB, BC is 2/3 of the segment, AC is 1/3. So what would that mean the length of AC would be? If the whole thing is 15, and AC is 1/3, BC is 2/3, we can figure out the length of each segment.
AC is 5.
Yeah, AC would be 5, and then how about BC? 10. BC is 2/3 of the way towards the opposite side. Okay. Another way to say that is the ratio of BC to AC. It's 10:5. Or what does that reduce to? 2:1. It's a 2:1 ratio. That's the same as saying 2/3 of the way across, like I just did. All right. So if you compare the long part of the segment on the median to the shorter part, they're going to be in a ratio of 2:1. One will be twice as big as the other. That's how you get that fact right there. So here's saying the same thing that I just did with numbers, except without using specific values. All right, so look at segment AP. AP is 2/3 of AD. Okay, AD is the median, and AP takes up 2/3, DP takes up 1/3. I could have written that too, but I didn't write DP. All right, let's look at BP. BP is 2/3 of segment BF. It's 2/3 of the way from B to F. And then CP is 2/3 of the segment CE. And that's exactly what I wrote. CP is 2/3 of EP. Okay, that's, I think this equation is more helpful than thinking about it as a 2:1 ratio. Sometimes, I think maybe the 2:1 ratio is easier for other things. It depends on what they're asking. But now if you gave me a value for, say, AD, say you told me AD is 12. Well, I could just fill 12 in for that, multiply by what's in the equation, and find AP. Right? Just solving an equation from Algebra 1. Okay, and here's what the centroid is physically. It's its balancing point. So if you were to take this triangle, cut it out, and you wanted to balance it, like on your finger, what you would do is you'd have to put your finger right on the centroid, and that's where the triangle would balance. Now, that does make a few assumptions that simplify the problem. We're assuming this triangle is made out of a material that's uniform. So in other words, it's not like part of the triangle is made out of heavier stuff on one side and then part of the triangle is lighter. It's a uniform material that the triangle is made out of, like a piece of paper. Right? It's uniform thickness, it's uniform density, it's pretty much the same material throughout. If you made it out of a material that wasn't uniform, that was heavier on one side than the other, then the centroid might not be the balancing point. Right? But that's what the centroid is. It's the balancing point. Right, so let's see if we can find some links here. Okay, they told us that P is the centroid. All right, so if we wanted, we could draw all kinds of congruent segments. I don't have everything labeled, but the segment, let's just call this A. RA and QA, those are congruent. QT and ST, those are congruent. And if we wanted to label that, RB and SB are congruent. Now, maybe we would use that fact if we were trying to do something with congruent triangles, but we don't need those for this problem. Okay, so how could we start? Let's find the length of RT. Okay, we know PT is 5. Anybody give me a... Yeah, let me fix that, actually. That's 5. Anybody give me an equation? Say, without numbers for now. Say, like, PT is what? It's going to have a fraction in there and then maybe another segment. Marquise?
2/3 of RT.
No, not quite. I don't think PT is the bigger part, but yeah, it's the 1/3. PT is 1/3 of RT. But now we know PT. How long is PT? They said it was 5. So let's fill that in. 5 equals 1/3 of RT. And how do I get rid of that 1/3? Multiply by the reciprocal, which is?
Multiply by 3 and then 1. And 15 equals RT.
Okay, so we got RT. 15 equals RT. Remember, when you want to write the measure of a segment, you just write the letters. You don't put the bar over it. If I wanted to talk about congruence, I'd be putting a bar over it and doing it that way. Okay, what about RP? Okay, if you're not sure, well, you know RT is 15. And you know to get RT, you got to add RP and PT. Or what do they call it? Yeah, RT. Yeah, they call it PT. What is that? Anybody tell me what postulate is this? RT equals RP plus PT. It's going to be on the midterm. Remember that? It was one of maybe way back in chapter 1. Yep, very good. That's the segment addition postulate. The total length is equal to the sum of the individual segments. Good. And now we know RT is 15. Oh, whoops, that's supposed to be RT equals RP. Sorry. But yes, you're still right. It's the segment addition postulate. RP plus PT. RP we don't know, or you might know in your head at this point, plus PT, that was given. So looking at that equation, what does RP have to be? 10. That's it. So find RT and RP. Got them both. Any questions on that? All right, this one. Find the coordinates of the centroid. In general, if I have you do this, I wouldn't pick just any triangle. I would try to make it so that things work out nicely with the coordinates. Because in general, these kind of things don't have to work out nice. All right, I want to find the exact coordinates of the centroid. What's the name of the segments that intersect to create the centroid? They're called the... Well, the segment name I'm thinking of, all these segments are concurrent in a point called the centroid, but what's the name of the segments that create the centroid? The medians, yep, medians. So, what's the definition of a median? It's a segment drawn from what to what? Yep.
The vertex to the midpoint of the segment.
Yeah, the vertex to the midpoint specifically of the opposite side. Yep. So, first thing we really have to do here is, let's draw one of the medians in. We only need one of them. Because once you have one of them drawn, then you can just measure 2/3 of the length, and then there's where your median goes. Okay? Let's try to find the midpoint of side LJ. Okay, we'll draw in that median. So we'll draw it from K to the midpoint of LJ. Okay, anybody remember how you find that? What does midpoint mean? Yeah.
The center of any given shape.
So what about for a segment?
Or it's cut exactly in half.
Yeah, or it's cut exactly in half. It's right in the middle. So if you've got endpoints and you want to find the middle, you average them. Right? So let's take 3 plus 7. Add them up. And what do I divide by to average them? Here? So how do we average them? So we're trying to find the midpoint of segment LJ. So we're trying to find what's in the middle of 3 and 7 and the middle of 6 and 10. We're going to find the midpoint of the x values. Then we'll find the midpoint of the y values. So how do I find the midpoint of my x values? One x value is 3. The other one is 7. Yeah, divide by 2. Okay, so everyone remember how to do that? Find the midpoint? If you have to find the midpoint between 2 points, you're just averaging your x's and averaging your y's. Right? Who can give me the y value? Just the formula for how I'd find the midpoint of the y's. Nathan?
It'd be 6 plus 10 over 2.
Yep, 6 plus 10 over 2. So the midpoint of LJ, 3 plus 7 is 10, over 2 is 5. 6 plus 10 is 16, divided by 2 is 8. So that's the midpoint. Okay. 5, 8. So 1, 2, 3, 4, 5. 4, 5, 6, 7, 8. Right there.
What's the what formula? Like without the number?
You could think of it as x1 plus x2 over 2 and y1 plus y2 over 2. Just average the x's and average the y's. Okay, what worked out nice here is it's a vertical line. My median. So that's going to make it easier to measure the length of it. Okay, so there's my median. What I'll do is I'll put that in a different color so we know it's the median. How long is that segment? How many units?
6.
6, and it's vertical. How do I know it's vertical? Well, I know the x value of k and the x value of my median are the same number. If the x values are the same, that gives you vertical lines, 2 points that are vertical. Okay. So let's label this A. So segment KA equals 6 units long. Now remember, the centroid is 2/3 of the distance from K towards A. So it's not all the way towards A, it's 2/3 of the way. So if something is 6 units long and you go 2/3 of the way, how far have you gone? Think if something's 6 miles away and you said, yeah, I'm 2/3 of the way there. How far have you gone? 4. Okay, you've gone 4 units away from your start point. So we started at K, we head towards A. What direction would I go in to head 4 units away from K? Up. 1, 2, 3, 4. Right there. That's my centroid. It's 2/3 of the distance between K and A, or you can think of that 2-to-1 ratio. Let's call this point B. From K to B is 4, B to A, 2. K to B is 2, B to A, the ratio is 2-to-1. From K to B and B to A, 2-to-1 ratio, 4 to 2. So just write down your coordinate. It's right 5, and then up 6. Here's the coordinates of your median, centroid. Any question how we found that? Okay, so not too bad. Right, let's look at our last special set of lines, set of segments. And these are the altitudes. Okay, so an altitude is a perpendicular drawn from a vertex to the opposite side. And as I said, it has to be perpendicular. So you draw a segment from a vertex perpendicular to the opposite side. So what's a little tricky about an altitude is it can lie inside the triangle. Sometimes when you measure the height, the altitude when you draw it will be completely inside the triangle. It could be on the triangle, right on one of the edges, or it could be outside the triangle. It depends. We're going to go through all 3 cases as an example. Okay, but like the perpendicular bisectors, like the angle bisectors, like the medians, the altitudes, they are also concurrent, or they all meet at a single point. And that point is called the orthocenter. All the altitudes meet at a point called the orthocenter. Okay, we'll look at, we've looked at some special properties. The orthocenter, we're not going to really do a lot with it. Okay, it's all kinds of special points and triangles and circles. And in fact, if you go online and you look up what's called the 9-point circle, it's a circle, kind of like what we've done with the in-center and circumcenter. It's another special circle. And there's 9 special points that are all on that circle. Some of the points are points you already know about. Okay. Honestly, I don't remember all 9, but I know some of the ones we've talked about so far are on that circle. Okay, maybe if we have time after, we'll look that up, the 9-point circle. Right, so actually, let's take a quick look at that 9-point circle. So here's the 9-point circle. And some of these points you guys know, we just talked about. the midpoint of each side of the triangle. So if you find all the midpoints, those are 3 of the points that this 9-point circle goes through. The foot of each altitude. The foot basically is the point where the altitude intersects the other side. Okay? We've talked about those as well. Okay? So you've got that. That's 3 more, so that gives you 6. And then you have this last one. Okay, I think that last one, that might be a little complicated, but it's the midpoint of the line segment between each vertex to the orthocenter. So we just talked about the orthocenter. The orthocenter is where all the altitudes meet. Well, if you find the orthocenter, put that point down, and then you draw in a line segment from each vertex to the orthocenter, the midpoint of that line segment, this is saying that is also the other 3 points. Okay? So that would be a little more complicated. But I'm thinking right here, this is the orthocenter. Right? Oops.
Whoa.
So there's your orthocenter. Right? And then if you draw in a segment from the vertex to the orthocenter and find its midpoint, that's one of them. We'll go over here now. And then if you draw in another segment from the vertex to the orthocenter, find its midpoint, right there. There's another one. And if you draw in a segment from the vertex to the orthocenter, right there, and find that midpoint, that's another one. Okay, so it's just a special circle. Those points, they're called concyclic points. Con is like with, cyclic is, think of it as a circle. They're 9 points on a circle, with a circle. All right. And there's a few other names. I'm familiar with Euler's. That's how you pronounce that, Euler's circle. Some of the other names, I haven't heard about those. Okay? But there's all kinds of special properties of this circle, things you can measure. But we're not going to get into it. But I hope everybody can kind of understand from what we studied this week, those 3 things. Should be able to understand those. Okay. Okay, let's start with an acute triangle. Anybody have a guess where the orthocenter is going to be for an acute triangle? Yep.
The center.
Right in the center?
Oh,
It could be. Could be. The orthocenter and the centroid could be the same.
well, it depends on if it's an equilateral acute triangle.
Okay, this won't be equilateral. It'll be like a scalene. So where do you think the orthocenter could be for a scalene?
Probably the bottom half.
So
Look at
inside?
scaling the top, like taller point of the tall point, and then when you draw the angle bisector, it's gonna be the bottom half.
Okay, so remember, we're not drawing bisectors here. We're drawing altitudes, right? From the vertex perpendicular. All right, so let's look at it. I did draw this one kind of, looks equilateral like the isosceles. But in general, all acute triangles are pretty much going to have the same pattern I'm about to show. So there's an altitude from the vertex perpendicular to the opposite side. I'm going to draw another one. So that's a 90. That's a 90. And, nope. Don't want to move stuff. Let's try that. And that's a 90.
The bottom half.
So there's your orthocenter. Okay, let's look at another acute triangle. This time, let me try to make it, this time it's not equilateral. Okay, I don't think that looks equilateral anymore. All right, so if we draw in our altitudes here, okay, if you look at what happens, some of the altitudes they might not end up inside the triangle. And actually, you know what, I got a better diagram I'll use for the next one. We'll do that right here. Okay, let's try a right triangle. Okay, let me start with my altitude from this side, perpendicular to the opposite side. Notice I can't draw it towards the middle where these segments would be bisected, because that would be a median, and it wouldn't be perpendicular. Okay, this would be more of a median now, if I drew it there. Okay, what about my other altitudes?
They're gonna be weird.
What's going to happen when I draw the other two?
You're gonna be right on the line.
Yeah, they're going to be right on the line. From the vertex, perpendicular to the other side. So let's do them in red. That one, and one more. From the vertex, perpendicular to the opposite side. So where's the orthocenter this time?
On the 90.
Yeah, right there. So in a right triangle, that's where your orthocenter is. It's on the 90-degree angle.
It also makes little 90 degrees if you look closer.
Yep. And now the obtuse triangle. Okay, so this is a little bit different. All right, let me start with the first altitude. From the vertex, okay, perpendicular to the other side. You know what? I'm going to extend it. I'm going to extend it pretty far down. And then let's try to move it. Okay. Any question on that one? Perpendicular. Now, the reason I had to put dotted lines and extend the other two sides of the triangles is because if I try to draw in my altitude from here, perpendicular to the other side, it's not perpendicular anywhere inside the triangle. I have to go outside the triangle on the extension of the side to make that happen. Yep.
Be too big.
So this one,
This looks like one of those diamond things.
Like that.
Where it's like,
It's not descriptive.
okay, maybe about right there. It's hard to get it perfect, but let's say that's about a 90. Okay, and we got one more. Drawing it from here, perpendicular to the opposite side. So this one, you know what? I think a couple of my angles are a little bit off because they should all meet at a point. So let's see if I can try to fix that a little bit. Actually, I think that looks a little better. This one up here, actually, I think it's not quite 90. So we'd have to come a little bit. See if I can fix it more like maybe like that, and then see if I can move it. Yeah, this one. Yeah, it's hard. It's hard to get it perfect, but try to get the idea. Okay, that definitely does not look 90. Let's see if we can adjust it. Okay, that looks a little bit better. But this is the hardest case to try to sketch. So let me see if I can fix it. All right, so we fixed our diagram. Okay, now each altitude is perpendicular. There's your 90, 90, 90, and they all meet right there. Okay, so this time Your ortho center is way outside the triangle, okay? Way outside. So you might have to extend the sides of your triangle like I did to try to get the ortho center. If you have something that you can measure with a 90-degree angle, like protractors, that'll help you make a more accurate sketch rather than trying to do it by eye. Okay? You could also construct a perpendicular. If you remember how to do that construction, that would also make it exact. Estimating it, as you can see, is somewhat difficult.
Are we gonna have to do this on the test?
I might ask you where the ortho center would be, yeah, for obtuse, right, or acute. Okay, so make sure you know that. So I would add that to your cheat sheet with in-center, circumcenter, centroid, all that stuff. Okay, any questions on that? Okay, so again, as far as applications to altitude, it is a point that helps you figure out other points on the nine-point circle, the ortho center, but we're not really going to be doing much with it. Yeah.
Yeah, that picture you just made.
Yeah.
Is there any way you can take that picture and reflect it over Phil?
Reflect it? Maybe after, we'll try.
Alright, because then it would look like a sick drawing.
All right, so the homework, it's on 282, 1 to 12, and 17 to 19, all.
Is simple